Hello everyone. So today we are going to break down two of the essential tools for visualizing high dimensional data, that is TSNE and UMAP. Okay, so let's get into it. Dimensionality reduction is a process of projecting data from hundreds and thousands of dimensions down to 2D or 3D, which we can actually see. Think of it like casting a 3D sculpture shadow on a wall. You lose some depth, but the right angle still reveals the shape. TSNE and UMAP find the perfect angle of your data, and beyond visualization, they also remove noise and can boost downstream the ML performance. Classical methods like PCA only captures the linear relationship, but real-world data images, text embedding, genomics live on curved non-linear surfaces. So for that we need TSNE and UMAP. TSNE introduced in 2008 converts high dimensional distance into probability that are arranged point in 2D so that probability matches. Close points stay closer and distant ones spread out. The key trick is that use a student's t distribution in the low d space instead of the Gaussian part. The heavier tail pushes moderately distant point further apart, preventing everything from collapsing into one dense blob. This is called as cloud fixing. Here, the one of the most important hyperparameter is perplexity. Think of it as the efficient number of neighbor per point. Typical range from 5 to 50, default 30. Low equals to tight local clustering, and high means losing global structure. Okay, here's a big warning that intercluster distance in TSNE are not meaningful. Two clusters look far apart in 2D and doesn't mean that they are far apart in the original data. Never interpret them as real distance. Moving forward to section 2, the UMAP, which was introduced in 2018, that's a serious upgrade in many ways. When TSNE work with probability distribution, UMAP is rooted in the topology and Riemannian geometry. It models your data as a fuzzy weight graph of nearest neighbor connections that find a low D layer that preserve that graph structure. The process of this goes like: find the k nearest neighbor for each point, assign edge weight using exponential delay, normalized it by each point local density, and then optimize a 2D layer out of it, matching the high D graph using cross entropy loss and the SGD loss also, which can give you a negative sample. Okay, this is bit confusing. If you repeat this part again, then you may get it to know again. The main hyperparameters here to know are n neighbor, that is default 15, low equals to local cluster, high equals to global shape. Second, min distance, default equals to 0.1, low equals to compact clump, high equals to more spread out. Third one is n component, default equals to 2, target dimension set higher for pre-processing. Fourth one is metric, default Euclidean, swap to cosine for text embedding. Okay, now one of the major advantage of UMAP over TSNE is that UMAP support out of sample transform. Train it once and you can project new data points into the same embedding later. TSNE can't do that. Moving forward to section 3, that is avoiding the mistakes, and some of the key takeaway are that use TSNE for smaller data set when cluster visualization is the only goal and speed doesn't matter. Use UMAP for the large data set when global structure matters and when you need fast iteration, or when you are using it for a pre-processing step for a downstream model. Common mistakes are, first of all, don't interrupt cluster size. These are the algorithm artifacts, so don't they are not the true density of it. Okay. Secondly, don't read into the intercluster distance, especially in the TSNE. Third part is, don't run TSNE just once, it's not deterministic. Run multiple seeds and compare. Fourth, don't stick to one perplexity or a n neighbor value. Try 5, 30, 50, and for perplexity 5, 15, and 50 for the n neighbors. Okay, and lastly, don't feed the raw pixel value straight into it. Just run the PCA down to 50 to 100 components first. Okay, so one of the most key takeaways that TSNE and UMAP are go-to non-linear method for manifold data. They are only be used for the visualization. UMAP is bit faster and preserve global structures and handle new data, making it stronger choice for the most real-world workflow. Okay, so this video is a bit smaller video as compared to other. The main part for the TSNE and UMAP is that you need to know is in the coding part, so we'll be covering it soon also. Thank you.